that's called a t-test. Okay, this is kind of a preview on something that we're really going to get into next week. Okay, yeah, I know the battery's low. We'll be done before that. Thanks. Thanks for the warning. Well, I know we're going to be done before that, so we're almost done. So hopefully I won't run out of power before that. I'll get this done a little bit quicker. Now this time, what I'm doing now is I'm comparing two means. One way of looking at this is to check a given value that we want to test and look to see if it's outside the confidence interval for what the data tells us that the mean should be. Well, similarly, we could do something called a t-test. That's hidden here under something called compare means. And I'm going to go compare means. I'm going to go to one sample t-test. I'm going to click on that, and it asks me for the test variable. It's only one variable, so we know we're going to be using that one. We can click into options. Again, it's 95% confidence interval is the only thing we have. Confidence interval is the only thing we need to choose there. And it has another box here where I can put the test value. The test value here is the mean that we're comparing our data to. In this case, it's going to be 57 point, what was it, 6, I think? I'm going to call it 57.6. My recollection is that's probably what it was. I am going to compare, and I'm going to calculate how many standard errors away from our point estimate, which is calculated from our sample, that this value 57.6 is. That's really what tells us what the likelihood that we would get a value based on what our test data was, our mean, the way that the data varies. This is going to tell us how likely it is, how many standard deviations away or unlikely it is that we would get a value of 57.6 if that with the data that we got for the population mean with the data that we got. I'm going to click OK. SPSS does its normal stuff. Comes up with, I'm going to repeat it so I can scroll a little, just so I can scroll up a little bit without moving things around the screen too much. So let's take a look at what this screen tells us. First of all, the mean is 57.27. We know that already. Standard deviation, our standard error, we calculated that before. Okay, this time it's telling us, gee, degrees of freedom is 7, right? And it's telling us that value, the difference between those two values, the mean that we found, the point estimate that we found, and that 57.6 is 5.5 standard errors difference, right? 0.6 times roughly 6 is going to be the difference between 57.25 and 57.6. Okay, that's the number standard, x bar minus mu over standard error, right? That's what that number t represents, basically. Okay, so it's 5.5 standard errors difference. How likely is that to occur? Well, that's so unlikely to occur that it will only occur 1/10 of 1% of the time. Okay, our significance, our two-tailed probability is 0.001. Okay, actually, it's even half of that, half in the upper end of the curve, half in of the normal distribution, half in the lower. Okay, now this is 95% confidence of the difference between the two means. In other words, you would expect the difference if the null hypothesis is true. Difference between the mean we calculate, the point estimate, and the mean that the manufacturer says should be 0. The difference. This is our 95% confidence interval for the difference, and it's noticed that they're both negative numbers, so 0 is not between these two. So we know that the difference is different than 0, meaning that the mean, and more confirmation that the means are different. So what do we have here? We have a probability of these two means being from the same population of less than 0.001. That's our p-value, the probability that we would get this kind of result, this big a difference, if we were wrong and it was really from the same population, that they really are the same, and we can't reject the null hypothesis. Well, when we use the confidence interval, we could only see whether to reject or accept the null hypothesis. Is the value we're comparing it to inside the confidence interval, so we can't say they're different, or is it outside of our confidence interval? So we can say we're 95% sure we're different. When we use this test, we can actually measure how probable this particular outcome is if we if we don't reject the null hypothesis, or if we reject the null hypothesis. Okay, if we reject the null hypothesis, we have a chance of being wrong of less than 1/10 of 1%. Okay, so not only do we know that our confidence is 5% chance of being wrong, now we know that it's even more unlikely that we would be wrong. So as long as this significance, our probability of being wrong, is less than 5% for a 95% confidence interval, 5% chance of being wrong, as long as this number is less than 5%, the t-score is big enough to give us a value less than 5%. We reject the null hypothesis that the two values are equal, and we accept the alternative hypothesis that they're different. Notice it does a two-tailed test. If we call this a one-tailed test, I would just simply double that number for my probability. Not often you're going to do a one-tailed test though. Okay, so let me see if there's any questions on that so far. Okay. The t-score is negative only because the way it used the data it was because our sample mean was a lower number than our test mean, right? So it was 57.27 minus the number we were testing against, which we were saying was the predicted mean, the null hypothesis mean, 57.6. So x bar minus mu, it was using this number for x bar. It was using 57.6 for the predicted population mean. So the number we started with, the number we're subtracting is bigger than the number we're subtracting from. So it came out negative. It really doesn't matter. If you reverse these two, it just become out t-score plus 5.508, 7 degrees of freedom, significance 0.001. So you get exactly the same result. You'd even get the confidence interval for the difference, which you're expecting to be 0, to be plus 0.18 to plus 0.46. Okay, it would just change the signs, but the result wouldn't be any different. And it is indicating that there's a difference, right? Because the probability of getting this big a difference between our mean that we calculated based on our sample and the mean that the manufacturer claims, mu, remember that test value. Remember I put in that test value? Analyze, compare means, one sample t-test. I put in the test value. This is what we think our population mean is. That's our null hypothesis, that mu is equal to 57.6. The mean for our test variable was 57.25 approximately. That's our x bar. So we're looking at how big that difference is in terms of number of standard errors difference. If this were a large sample and the t-test came out to be 1.96, this significance, two-tailed significance, would come out to be exactly 0.05. Again, looking at our normal distribution. Okay, that you don't have to worry about that making too much sense now. As we work with this more, it's going to make more sense. So that's how we do hypothesis testing. We propose a hypothesis that these two means, that this mean is equal to this alternative hypothesis, that it's different than that value, and we try and prove that we're 95% sure that the two means really are different. That mean for that mean that's predicted for the population is really outside that range that we feel comfortable saying that we're 95% sure that the real mean is. Okay, so that's what we're doing. We propose it in a formal manner by proposing a null and alternative hypothesis. And the terminology is that if we can't prove with 95% certainty or 95% chance of being wrong, even if it's 94% certain and only 6% chance of being wrong, what we say is we fail to reject the null hypothesis. We don't say the null hypothesis is true. We don't say we accept the null hypothesis. We only say we failed to reject the null hypothesis. If we can say with 95% certainty, 5% chance of being wrong, that the two values are different, the mean and the mean we're predicting and the mean that we calculate based on our sample are different. We can say that with 95% confidence, then we reject the null hypothesis that the two means are the same and accept the alternative that they're different. Okay, a little bit of linguistics there, but it, it's meaningful, right? Because even though we fail to reject the null hypothesis, doesn't mean that we're accepting that it's true. It just means that we don't have enough information to reject it. Because really, all we know is it's within our 95% confidence interval. But remember, depending on what our level of confidence might be, if we change it to 90% or 99%, that range could change. And if we have a different sample size, it could dramatically change that range. So the same analysis might come out with a different conclusion if we had a larger sample or we were willing to accept a different level of confidence. Okay, so I think that's okay for tonight. I think also that'll help you go through the rest of the problems and stuff like that. They're awfully similar, except for the fact again with the proportions. The only difference is the up. Look, I got warning up there. The only difference is that with the proportions, you have a different way of calculating the standard error. So don't let it confuse you. It's the probability, the p-value, right? 0.3, 0.1, 0.15, whatever it is, zero point 0.5 times 1 minus p, which would be just 1 minus whatever that is, like if it's 30% would be 70% of 0.3 times 0.7, divided by the sample size, whatever it happens to be, 10 people, 20 people, 100 people, right? And then you take square root of the whole thing, unlike the way you would do it with a scalar variable, where it's the standard deviation of your sample divided by the square root of the sample size. Okay, use them. It's a corollary operation, and so don't let that confuse you. And keep in mind that if you have a sample that's larger than 30, you can use the z-score instead of using the t-table, which would mean that for your z value, you would use 1.96 for 95% confidence interval. If your sample size is less than 30 and you don't know the population standard deviation, well, then you have to use the t-table. Okay, so let's call it a night, and hopefully that'll